Edexcel Core Pure, Complex Numbers 5, Complex Roots. Solving equations. So we've previously seen how we can solve the following types of equations. So we've looked at z to the n equals 1, where we looked at the nth roots of unity, and we've previously looked at z to the n equals w, where w is any complex number including a wholly real number. So these are the same as finding the nth roots, or if you'd like to think of it as solving an equation, we can think of it as solving z to the n minus w equals 0 and thinking of this as an equation. So in this problem, the equilateral triangle will be formed on this eigendiagram that has a centre at 2 plus 3i and one of the vertices is at 4 plus 3i, and we're trying to write down the equation whose solutions could be represented by these vertices. So for example, 4 plus 3i is one of the solutions, and we're trying to draw a diagram that would represent all three solutions. Well, if we are looking at an equation with three solutions, then that suggests we're going to be looking at cubed roots of a complex number, and those cubed roots we would expect to form the vertices of an equilateral triangle. So we're going to try and find the equation that would have those vertices. So one of the roots is 4 plus 3i, and the circle is centred at A. So we need to form an equation where z minus 2 plus 3i cubed is some complex number called w. We know that one of the roots of this equation is 4 plus 3i. So substituting that into this equation, we're going to get 4 plus 3i minus 2 plus 3i cubed is w, and this gives me 2 cubed is w. Therefore the number we're looking for is wholly real, and it is 8. So the equation that would represent this scenario would be z minus 2 plus 3i cubed equals 8. So if you are given this equation in a problem, you may be expected to produce that diagram and show that the roots would lie on the circle and form an equilateral triangle. So we knew we were looking for three roots, so we've gone for z minus the centre cubed equals some unknown number w, and by substituting the given root we were able to find that w was indeed 8. So we know that this equation will have three solutions, and that those three solutions lie on the circumference of a circle centred at the point 2, 3. So now if we think about solving this for z, the first thing we need to do is to write 8 in its modulus argument form. So we can now write this as 8 is exactly the same as, and the modulus is 8, and if it's the real number 8, which it is, then we can write this as cos 0 plus I sine 0. Its argument will be 0. So now we are ready to think about taking the cubed root of both sides, and that will require the application of de Moivre's theorem as well. So the left hand side, when I take cubed roots, simply becomes z minus 2 plus 3i equals, so we're going to have to cube root the 8, and before we can fully cube root the right hand side we need to make sure that we have generalized this angle as 0 plus a multiple of 2 pi plus I sine 0 plus a multiple of 2 pi, And then when we apply de Moivre's theorem, we will get a third. And this will give us the 3 roots that we are looking for. So simplifying this a little bit more now, we've got z minus 2 plus 3i is exactly the same as 2, and just tidying up this bracket a little bit, it's cos 2k pi over 3 plus I sine 2k pi over 3. And we're now going to look at k is 0, 1 or 2. So when k is 0, we would have z minus 2 plus 3i is exactly the same as 2. In other words, z equals 4 plus 3i. So that's the root that we knew about earlier on. So let's see if we can find the other 2 roots now. So let's try k is 1. So that gives us z minus 2 plus 3i equals, and when k is 1, we get 2 cos 2 pi over 3 plus I sine 2 pi over 3, and when we simplify that, it equals minus 1 plus root 3i, and then if we make z the subject, we'll have z equals 1 plus, and collecting the imaginary parts together, 3 plus root 3i. So there's the second of our roots. I'll call that one z2 so we can distinguish it from z1, and we can now look for z3. So now when k is 2, we get z minus 2 plus 3i is 2 cos 4 pi by 3 plus I sine 4 pi by 3. Which simplifies to minus 1 minus root 3i, and therefore we can rearrange for our third solution, which I'm going to call z3, and z3 is 1 plus, and collecting the imaginary parts together, we get 3 minus root 3i. So we now have the 3 solutions to the original problem. So the key step before we apply de Moivre's theorem is to write 8 in modulus argument form, and in particular to make sure that we've got the extra 2k pi to give us the required 3 solutions. Then when we apply de Moivre, we get the cubed root of 8, and we get a third of the argument, and we can let k equal 0, 1 or 2. When k was 0, we got the solution we were given originally. When k was 1 and we rearranged for z, we got the second solution, and when k is 2, we got a third solution. And we can see those on the diagram. So there's the original value for z, there's the centre of the circle, and now we have the 2 extra solutions to the problem. And that brings us to the end of complex numbers 5.